Welcome to 38th lecture on numerical analysis. We are studying solutions of ODEs, and in last lecture we studied Runge method to solve first order ODEs. In this lecture we'll solve another example. Here is the highlight of the method. We are given the differential equation dy by dx is equal to f of xy and an initial condition y of x naught, and we are also given the step size h, and y for any n plus h is based on yn. This means we start from the initial condition x naught and we keep on jumping, and each jump is of size h unless we reach to the value of x for which we are asked to find y. So we start with the initial condition, we keep on jumping, and each jump is of size h unless we reach to the value of x for which we have to find y. So we have to find y of x, right? And for each jump we have to calculate these 4 k's: k1, k2, k3 and k4. H is given and yn would be the initial value. If we start from x naught, that would be y of x naught, that would be given y naught, and will keep on moving unless we reach to our destination. K1, K2, K3 and K4 are computed using these fixed formulas. K1 is f of x and yn. This n is the value of n for which working. Initially that would be the value x naught, and then that would be x naught plus h, and then x naught plus 2h, etc. And K2 is computed using this formula, xn plus h by 2, the halfway from xn to the next, from xn to xn plus h, the midway between that. And this k1 is fed here, and this k2 is fed here, and this k3 is fed here. And these formulas are simple, but we have to calculate these values k1, k2, k3 and k4 for each step, right? So here is an example. We are given dy by dx is equal to 10x, and the initial condition y of 0 is equal to 1, and we are also given the step size h is 0.25. We need to find the value of y at x is equal to 0.5. This means that we'll start from 0. We'll take the first step, and the step size would be 0.25, so that would take us to 0.25, and then we will take another jump and we'll reach to the desired value of x 0.5 for which we have to calculate y. So in this case we'll have to make 2 jumps. So we'll start from 0. So let's start from 0. N is equal to 0. Y of 0.25 is y of 0 plus h by 6, these k's, and y of 0 is given. Y of 0 is given to be 1, and h is also given 0.25. so we need to calculate k's. So k1 is f of x naught, y naught. Why x naught and y naught? Because in general this is x and yn, and n is equal to 0 here, therefore we have replaced n with zeros. So f of x 0 by 0 is f of 0 1, f of xy is dy by dx is 10x. So actually this is f of xy is equal to dy by dx is equal to 10x. So if we put x, if we compute f of 0 1, f of 0 1, this means we'll replace x with 0 and y with 1. So if we replace x with 0, y isn't there, that becomes 10 times 0 is 0. So we compute k2, that is x naught plus h by 2. X naught is 0, h is 0.25, 0.25 divided by 2, plus y naught is 1, plus 0.25 divided by 2 multiplied by k1, because this is the k1 we'll feed here. And we'll keep on doing, and we calculate k2, k3 and k4, and finally y is 0.25, that is 1.3125. that is actually this value. Y of 0 is a 1, y of 1 is 1.3125. we have reached here 1.3125, and y of 0 is equal to 1. So and we need to go to this point. So we have taken the first jump to 0. And for this is for n is equal to 0, we have starting from n is equal to 0, we have reach to y 0.25, and then we'll start from 0.25. We'll try to reach to 0.5 by taking a jump equal to 0.25. So x of 0.25 is 25, and 0.25, y is 0.25. We have just calculated this is 1.3125, and now we plug the same things in this formula, and y of 0.5 is y of 0.25 plus h by 6 times this, and we know h, we know y of 0.25 we computed in last step. Y of 0.25 was computed in the last step, that is 1.3125. We'll plug that here and we'll calculate these k's again. K1, K2, f of K1 is f of x n by n, n is 0.25, x of 0.25, y of 0.25, that is 0.25, y of 0.25 is 1.3125, and we know that f of xy is 10x, f of xy is 10x, here this one, f of xy is 10x, therefore f of 0.25, 1.05 is 10 multiplied by 0.25, 0.25, this becomes 2.5, and in a similar way we can calculate k2, k3 and k4, and y of 0.5 turns out to be 2.25. so let's check whether this result is accurate and how accurate it is. The exact solution that we studied in the last course, complex, the subject linear algebra and differential equations, we studied that this is a variable separable type of differential equation. So we can take dx here and then we can integrate, it becomes 5x squared plus c, and we put and we can put initial condition then x0, for x equal to 0 y is 1. So if you put x equal to 0 y is 1, so c comes out to be 1. This means y of x is 5x squared plus 1. So if you put x equal to 0.5 here, the answer comes out to be 2.25, the exact solution. But let's see what is our approximate solution using Runge-Kutta's method. It is also 2.25. So this means the percentage error is 0. It's a very reliable method, the Runge-Kutta's method. Right, that's all for this lecture.